Have you ever just stopped mid-game and stared at the world on your screen? Or, wondered how animated movies create these places that feel so real? Well, it's not magic, it's math. And that's what this explainer is all about. We're going to pull back the curtain and look at the actual equations that build the pixels behind all those incredible 3D graphics.
So, right, this is the big question. How do we get from a bunch of abstract numbers and formulas to a living, breathing 3D scene like this one? We're going to tackle that today, and we're going to build the whole concept from the ground up, starting with the absolute simplest piece of the puzzle.
Okay, so it all kicks off with a really simple idea. Just take a look at this dolphin. At first glance, it looks like this complex, smooth, curved shape, doesn't it? But if you could zoom way in, you'd see it's actually built from hundreds or even thousands of tiny, flat triangles. And that's the fundamental secret behind almost every 3D model you've ever seen. So that's our first problem to solve. How does a computer even begin to see all these triangles floating in a 3D space?
Our journey really starts with this one core problem in all of computer graphics. How do we take a virtual 3D world and flatten it into the 2D image that you're looking at on your screen right now? Let's unpack that whole process.
Well, it helps to think about how our own eyes work, right? Light bounces off stuff and goes into our eyes. A computer could simulate that, but honestly, it's way more efficient to just work backwards. So it starts from a virtual camera, our viewpoint, and shoots a straight line of sight out into the scene to see what it hits. We call that line a ray. And this whole idea is the basis for an amazing rendering technique called ray tracing.
So, to create that virtual line of sight, we need a mathematical tool. We call it a ray, and it is the absolute foundation of how a virtual camera is going to see the world.
Now, you might remember from geometry class that a ray is a line that starts at one point and just goes on forever. But for us, in computer graphics, we have to be a little more specific. Our ray is a directed line segment. That means it has a definite starting point, a clear direction, and, this is important, a finite length. It's basically a vector, a little arrow that describes both a direction and a distance.
And this is how we describe that ray with math. It's called its parametric equation. Now, I know it might look a little intimidating, but it's actually really simple. P0, that's just the starting point of our ray. D is just a vector pointing in the direction it's going. The real magic here is the little t. Think of t as a slider. As you slide t from 0 to 1, this equation gives you every single point along that ray, from its beginning to its end. It's a super simple formula that lets us travel along our line of sight.
All right, so we have our virtual eye line, the ray. But a line of sight isn't very useful if there's nothing to see, right? So the next step is to build a world for that ray to travel through. And we do that using simple mathematical shapes we call geometric primitives.
You can think of primitives as the Lego bricks of the 3D world. They're the absolute simplest shapes that a computer can easily understand and do math on. And we use them to build, well, everything else.
Let's start with one of the simplest primitives out there, the sphere. Mathematically, it's really elegant. It's just all the points in space that are the exact same distance, the radius r, away from a single center point C. Just one clean equation gives you this perfect shape.
Next up is the plane, basically a perfectly flat surface that goes on forever. Its position is defined by just two things: any random point that sits on the plane and something called a normal vector, which you see here as n. That's just a little vector that points straight out from the surface at a 90-degree angle. And it's so important because it tells us which way the plane is facing.
And that brings us right back to the star of the show, the triangle. Spheres and planes are great, but pretty much every complex object you see, from a character in a game to that dolphin we saw earlier, is built from a mesh of triangles. They are the universal language of 3D modeling.
Okay, let's take a quick pause. We've got our ray, our line of sight, and we've got a world full of these mathematical shapes. Now for the main event, figuring out if, and more importantly, where our ray actually hits something.
And that's a great question, right? We can see it with our eyes, but how does a computer solve this? It only understands numbers. It can't see a collision. It has to calculate it.
The answer is something called intersection tests. This is where the magic happens. We literally take the equation for our ray, combine it with the equation for our shape, like the sphere, and try to solve for a point that exists on both. If we can find a solution, boom, we've got a hit. Now, to run these tests super fast, we use a few key mathematical tools, and one of the most important is called the dot product. It's a pretty simple operation. You give it two vectors, and it spits back a single number.
And that one number is incredibly useful because it tells you how much those two vectors are pointing in the same direction.
And this concept is used everywhere. For example, how does a game know if an enemy is in front of you or behind you? It uses the dot product. It takes your forward direction and the direction to the enemy. If the dot product is positive, they're in front. If it's negative, they're behind. Simple as that. We use this exact same logic to see if a triangle is even facing our camera. If it's facing away, why bother trying to see if we hit it? It's a huge time saver.
Okay, we can now cast a ray and find where it hits a single object. That's awesome. But a world isn't just one object sitting at the center of the universe. We need a way to place, rotate, and scale all of our objects to assemble a complete scene.
Now, to move things around, we use a tool called a matrix. It's just a grid of numbers that transforms coordinates. But this is where we run into a really fascinating problem. A standard 3x3 matrix can rotate an object and scale it up or down perfectly. But, mathematically, it is literally incapable of moving it away from the center of the world, a point we call the origin.
So what's the solution? It's an absolutely brilliant mathematical hack called homogeneous coordinates. To solve the moving problem, we just add a fourth dimension. By representing our 3D points with a fourth number, w, we can use a bigger 4x4 matrix. And this new matrix can handle movement, rotation, and scaling all in one single elegant operation. It's a beautiful, beautiful trick.
And as if that wasn't cool enough, this 4D system has another massive benefit. It makes creating realistic perspective almost easy. That fourth W coordinate can be used to make objects that are farther away from the camera automatically appear smaller on our 2D screen, perfectly mimicking how we see things in the real world.
Okay, so let's just recap the entire pipeline we've built. Step 1, we cast a ray out from our virtual camera. Step 2, we build a world for it to travel through using our primitive shapes. Step 3, we use intersection math with cool tools like the dot product to find exactly what that ray hits. And finally, step 4, we use the power of those 4x4 matrices to put every single object in its proper place to build our final scene.
We've just built an incredible mathematical machine that can see a 3D world. We know what our camera is looking at, and we know the exact point it hits an object. But that leaves us with a final, really big question. Once we have that hit point, so what? How do we figure out its color or its texture? What happens when light bounces around and creates shadows? That is the next layer of the simulation.